I was going to say extra chores would, make you think that there would be some to start with. All right. Yeah, no, that probably isn't it. So let's talk about what are, and you don't need to write this down right now, but just to give us an overview of what's going to happen here. Our focus is on derivatives and equations with derivatives, and that's why yesterday we went over these new rules. So now we have rules that will accommodate all the different types of functions you've learned about through your high school career. Polynomial functions, and well, not all of them yet. We'll get some more in chapter 3, but the basic functions, polynomial functions and exponential functions and log functions and trig functions, and that takes care of kind of those. Now what we haven't gotten to are like rational functions where you have a polynomial divided by a polynomial, or where we said multiplying, like if you took x cubed times sine x, how do you do that derivative? So we've got some special rules we have to do there, and then what happens if you have a trig rule inside of an exponential function? We haven't dealt with that. So I mean there's all kinds of those kind of situations we have to deal with, but the basic function rules we went over yesterday. Okay, so we want to now combine that with what we learned in chapter 1 with the chart, all the local max min and all the chart kind of things and those kind of situations, and put that in there. Then there are a couple other new things that involve derivatives we want to do as well. So the first thing is, and this is the new thing we're going to do, is this thing called differential equations, which we'll get to a little later. You can write that down later. We're going to be talking about something called a differential equation. Okay. So that's going to be something that will be on this next quiz. And then we're going to talk today about global max and min, which is different than local max and min. Okay, so we'll be talking about that. And then we're going to be talking again more about chart stuff, okay, which is just a continuation of what was on this last quiz, where we had to do local max min, or where the function's increasing and decreasing, do a number line, that kind of thing. Except now we'll do it with trig functions, and we'll do it with exponential and log functions, now that we've learned those rules. And then the last thing is just, again, your basic derivative and antiderivative kind of rules, which is a lot of what this homework was today. So those are the 4 main things. 2 of those aren't really new, and 2 of those we still have to talk about. So the first 2, differential equations, global max min, is what we're going to focus on today. All right, this derivatives and antiderivatives, we're going to check over your homework here and talk about this in some detail. And then, of course, this stuff with the chart, with the number line and stuff, is stuff we've already done. Just haven't done it like with the trig as much. Now, you did today. That was 10 through 13, right? 10 through 13, there was a trig equation. We started it for you yesterday, and you had some chart kind of questions on that one. Now, we're probably not going to do that one in class today, but we will talk about what we're going to go through one that's similar. Okay, we'll talk about that in a little bit. All right. So let's start by going over the homework. And so what's one? Allie, you got one you'd like to look at? Let's pick one out. On 2.6 or 2.7? Tell me what the function is. And this is an antiderivative one. It's a second derivative one. So you'd already done the derivative once. Okay, so give me the original function. Let's just go through the whole thing. And that was problem number 18. So the function is 2 times 3 to the x minus 1. That's it? Okay, so that was the original problem. So number 24 was to do the derivative of that, right? Oh, 18, right. 18 was to do the derivative of that. So if we pull up our notes from yesterday, so we've got our derivative rules, and so that would be this rule right here, right? Because it's 3 raised to an x. So we have this rule here, 3 raised to an x. So we're going to have 3 raised to an x. The minus 1 doesn't matter, right? The x minus 1 is just a shift to the right. The inside, that's the inside. The stuff here with the x is the inside. And we said the inside always stays the same, right? The inside always stays the same when you're doing a derivative. So a shift, those kind of things, that will be not only in the original function, but also be in the derivative. It'll also be in the antiderivative. The inside never changes, okay? So that's what we're looking at. And we're also going to have to tack on an ln, what in this one? 3. Because the base is a 3, we're going to tack on an ln 3. All right, so when we go to this one, and then we also have the rule that says when you got a number hanging out in front, right here, you got a number hanging out in front of the function, that's just going to hang around as well. All right, so this 2 is just going to hang out there, and then the rule is going to be the derivative is its own derivative. That's what exponential functions are. If it's b to the x, it'll be b to the x in the derivative, and then we're going to tack on the ln 3. So that's 18. So then 24 was do the second derivative, right? Right? So that means do the derivative of that. Well, ln 3, and to be honest, these that we're doing here rarely come up that much. I mean, we do run into them from time to time, but these are almost a little more complicated than a lot of the derivatives we work with most of the time. They're almost generally easier, but this is, we start with these actually just so we really focus on the rules. What does the rule say, and how do we put together these different rules? So what we got to recognize that ln 3 is just a number and 2 is just a number, and they're multiplied times the function. It's perfectly fine to leave your answer like this, but what you'll find is it's often important or helpful to rearrange it if you're going to use it more later. I mean, if all you're going to do is do number 18 and give your answer, then just leave it like that. That's fine. Rearrange, I don't care about rearranging. Okay, if you're just rearranging terms, that's whatever. That doesn't really matter. But if we're going to then use it again, which we are now, then rearranging can help. For example, what I would probably do is the 2 and the ln 3, I would probably put together in front and then do that. Because then that just helps me with the next one. Because now what I do is I look at that and I say, oh, that's just going to have that's just a number that's hanging out in front. So the rule says that's just going to continue to hang out in front. Right? And then I'm going to do the derivative of this. Well, what's the rule say? Well, it's going to stay the same. And we're going to tack on a ln 3. And now I would say leave it. That's fine. Now, if you want to do ln 3 times ln 3, which is ln 3 quantity squared, I guess you could do that. But it doesn't really have to. It's not necessary. You can just leave it right there. But the key is to remember that ln 3 is just a number. This isn't ln x, right? We're not going to go back, and I think we did that one yesterday where we kind of talked about it. We're not going to be using this rule there, right? ln x is different than ln 3. ln x is a function. ln 3 is a constant. ln 3 is a number. Okay? Yes?
Since it's just a number, why, when you do the derivative, doesn't it turn to 1?
Actually, I think what you mean is turn to 0, right? Because the derivative of a constant is 0. Okay, that's a good question. Let's discuss that. It's because of multiply as opposed to add. That's the whole key. If I have a function here, right here would be a great example. 3x to the 4th plus 8. When I go to do the derivative, if we did that, whenever we saw a number made the derivative 0, what would happen here? It wouldn't be 12x squared, because what's the derivative of 3? You see what I'm saying? If it's multiplied, if we just did the derivative of 3 and said that's 0 and then took it times that, everything would be 0 all the time, right? Everything would disappear. And so that's why when we multiply, we don't look at it that way. So the 3 just hangs, so this 3 just hangs out here, and we do the derivative and it stays there. But when we do the derivative of 8, because it's added all by itself, then that is 0. That's the difference. Oh, question mark? I thought you had. Okay. So, right? So there we go. So that is the difference. But I have seen that. That's not a bad question. For some reason, we don't do it when we see one like this. But yet I'll see people do this when they get 3 sine x, and they'll think, oh, derivative of 3 is 0, and all of a sudden they get 0 for it. And that's not what happens. All right. So, and then I think you had to do the antiderivative, right? On the later one. So let's talk about that. So the antiderivative. Now, I think we kind of went through this a little bit yesterday, but let's talk about it again. When you do the antiderivative, now it's more of a guess and check. That's the key. So what you do, when I say guess, what you're going to do is you're going to think of the rule. You're going to you want to come up with a starting point. So you want to come up with something that you think it might be, or at least reasonably close, and then do your check. Then do the derivative, and then see what's missing, because usually something's missing. And then you say, well, how can I get the part that's missing, and then you come up with that way. Now, once you've done that a few times, you just kind of will start to see them, and some of you might be seeing them already. But that's kind of the process. So what I would do if I'm looking for this and looking for the antiderivative, I got to think, well, what must have been here? So when I did the derivative, this was here. Well, I know if there was a 2 hanging out, I know there must have been a 2 hanging out in the original, because that's what it does. It just hangs out. Okay? So that must have been it. And I also know that an exponential is its own derivative. So I know 3 raised to an x, the original must have been that same thing. Just like in all these, it's still there. So I know that must have been there. Now I also know there's something about this ln3 that's going to have to kick out. And that's not there. Well, I'm not going to worry about that right now. I'm just going to say, well, maybe the original was this. I know it's probably not, but I think I'm in the ballpark. So I'm going to say, let's say the original was this. So now let's check it. Let's do the derivative. Well, actually, we already did, didn't we? The derivative would be the 2 would hang out there. The 3 to the x minus 1 would be there. And then I'd have to tack on this ln3. And I look at that and I say, well, is that what I got? No. I got this extra ln3. So there must have been something on here that made that ln3 not be there. Well, what was it? A 1 over ln3. There must have been a 1 over ln3, because remember, that's just a number. So it would have just been hanging out just like the 2. So there must have been a 1 over ln3 hanging out there, so that when I put on this ln3, let me put that 1 over ln3 there. Now when I put on that ln3 that the derivative rule tells me to do, it would have canceled. And so that's how you come up with that. And then don't forget the plus c. Right? Whenever we do an antiderivative, we throw on the constant, because remember, the reason for that is, like Ryan was saying with the 0, when we do the derivative, there could have been a constant added on there that then disappeared, right, when we did the derivative. So anytime we do an antiderivative, there might have been some constant on the unit. Okay? All right. What else? Uh-huh. What was 16? Plus e. All right? There's a 2 where? Maybe that's a different one. I don't know. That's okay. What the heck? So all your answers would have a 2 then, right? If you hang it out. So that's fine. All right. So we're going to do f prime. Now again, I'll admit, I've never seen the function x to e except in this problem. Right? The rest of you have never seen it. But again, it makes us think about the rule. Okay? E to the x is an exponential. It's its own derivative. And we don't tack on anything. If we did, it'd be an ln e, but we know that's 1. And then this is a power rule, because it is x raised to a number. So what the reason the authors put this problem in here is it really helps to point out the difference between these two functions. This is an exponential function when the x is up here. This is a power rule when the x is down here. So this means, and e is just a number. So we're going to bring e down in front, and we're going to drop that power by 1, which would be that right there. And then what's the derivative of e? 0, because it's just a number. See, and then that points out the difference between e and e to the x. E to the x is a function. E is just a number. All right, so that's not even there. All right, then we did a later one where we did the second derivative. So the derivative of e to the x is e to the x. Now, what's this? Well, that's just a number that's going to hang out there. So the e is going to hang out there, and then we're going to bring down the e minus 1. And then we're going to drop the power by 1. So that's e minus 2. And that's the second derivative. Now, I can distribute this e through there. That'd be fine, but it's not really necessary. Make sure you got parentheses around that, though. Okay. And then I'm guessing you had to do this, right? antiderivative. So antiderivative is e to the x, because the derivative would be e to the x. Okay, so that's nice. X to the e. Now, what did we say here? We know the power's got to be 1 bigger. So that's going to be x e plus 1. And then we talked about dividing by that new power, right? Because what's going to happen if you do the derivative, you bring the e plus 1 down in front, that'll cancel that. And then, so that's what that would look like. And then what's an antiderivative of e? Careful. E times x, right, which is different than e to x, right? E times x. So like the antiderivative of 7 would be 7x. The antiderivative of e would be e times x, and then plus sometimes. Okay? So, just kind of guess and check and try things and with these. This is going to be a small part of the next quiz. If the next quiz is worth, now the quiz you guys took was worth like 49 points. I mean, that was a pretty big quiz with a lot of stuff in it. This quiz is probably more 30-ish. Out of those points, this is probably 4 points, okay, on the next quiz. Now, I say that. It's more than that because in a max-min problem, you have to do the derivative and set it equal to 0. So you're going to have to know the derivative rules there. So the derivative's involved in a lot of the points, I guess. But as far as these kind of strange ones where I want you to do an antiderivative or something like that, especially antiderivative will probably be a very small part of the quiz. A couple, 2 or 3, 4 points, something like that. Okay, derivatives be more. All right. Anything else? Now, at 10 through 13, I don't want to get into that one really, just because we're going to do some more like that. If you've got some, we started it yesterday, so if you had some trouble, now I did notice as I was going along, some of you did not have much work shown there, right? I mean, you should have. You got to do the derivative set equal 0 for the inflection point. You got to do the second derivative and set it equal to 0, right? And so there's a number line. You should have 2 different number lines in that group, right? One for your max min, one for your inflection points. But we'll be getting into some more practice on those as we go along. All right. Well, if there aren't any other questions, then let's go ahead and get started kind of with some notes then on some of this new stuff, and hopefully give you a little bit of time to try to do a little bit of work. Probably not important that we write that right now. In fact, let's just do it. Okay, so this is actually section 2.5. So yesterday we went over those equation solving worksheet where we've got to do an equation, we got to solve it, right? And all the different types, algebraic equations, and trig equations, log equations, exponential equations, we've got to be able to solve it. Because those come up in max min problems. We're going to talk about a different type of equation today. So this is a little bit of just an odd topic that is really disconnected from max and mins and chart and stuff like that. But it is connected to what we're doing because it involves derivatives. And so that's why we're talking about it now. Differential equation. Now in college, if you were going to go into engineering, or a math kind of degree, probably, I'm trying to think where else you might, but mostly an engineering kind of thing, you would take calculus, and there would be 3 semesters, right? We're going to cover 1 semester of college calculus, plus get into a little bit of second semester. And then you would take a 3rd semester of calculus, which would involve 3 dimensions, 3-dimensional kinds of things. And then the next course you would take would be, the next math course you take would be differential equations. And the whole course would be about solving differential equations. So think about that worksheet we did yesterday. We were solving a bunch of different types of equations, algebra, trig, exponential, log type equations. We're going to solve differential equations. Well, what's a differential equation? Well, first of all, it's an equation that contains derivative. Right? I mean, what's an equation? What's it take for something to be an equation? It's got to equal something. And so differential, the word differentiable kind of goes with derivative, right? We talk about a function's differentiable if its derivative exists. Talk about the difference quotient, right? That's part of the definition of the derivative. So differential equation means equation that has a derivative. Just like an exponential equation is an equation that has an exponential function. A log equation is an equation that has a log function. Okay? Differential equation that has derivatives in it. But this is the difference. When you solve an equation like the worksheet we had yesterday, what's your answer? And it's a number. Yeah, like 7. Right? It's a number. Or multiple numbers. There might be 2 answers or 4 answers or 7 answers on the one we had yesterday, right? Or infinite answers. But it's a number. We get a numeric solution to all those kinds of equations. A differential equation is different. The solution, and this is where we have to kind of change our mindset here a little bit. I think this is what makes differential equations confusing at first, is we have trouble getting out of that old mindset of what an equation is, or the solution to equation. The solution to a, and then we abbreviate these DE. You'll see these referred in the book all the time as DEs, differential equation. The solution to a differential equation is the original function. We'll just put a y there. It's not always a y. It could be other things. For some reason, differential equation, we use y a lot more than we use f. We don't use f notation as much for our functions when we do differential equations. It's a lot more of y. Okay? It's the original function. So that's strange. So the solution to a differential equation might be like y equals x squared. Right? And it's just really hard to wrap your mind around, because you're so used to solutions being x equals 2 or x equals 7. It's the original function y. Now, so those are 2 important things you got to know. What is a differential equation and what the solution to a differential equation is. It's the original function. All right. There's 3 main types we're going to talk about. The first type is a differential equation that we can solve by taking the antiderivative. So that's one of the reasons we talk about antiderivatives right now. I remember I had a student once who was having a UNK professor help them. They were friends with a UNK professor, and he thought our book was really strange. He'd never seen antiderivatives talked about so early when you're first doing derivatives. And he'd never seen a book like that. And so I had a nice conversation with him about why we do it and what goes on. He says, that's a great idea. I love that. And then I don't know that he started using the book. They did, I don't think. But anyway, he thought that was a really good idea. Which was kind of interesting. But that's one of the reasons we talk about now, because now we can talk about differential equation. A differential equation we can solve by taking the antiderivative. So I would say to you, we've already done some of this. We just didn't call it differential equations. So let's do a couple quick examples. Y prime equals 3x squared. Is that a differential equation? Is it an equation? Does it have a derivative in it? It's a differential equation. Right? That's what it means. Differential equation is an equation that has a derivative in it. It's got a derivative, it's got an equal sign in it. It's a differential equation. The solution to that is the original function y. So the solution to this is what y is. Well, how do you go from y prime to y? Antiderivative, right? And we can do that. So what is the antiderivative? X cubed plus c. That would be the solution to that differential equation. So we've already done it. I just didn't put it in those words. We just said take the antiderivative of this function. Okay? That would be kind of like me giving you this problem. Don't write this down. But if I gave you x plus 2 equals 6, and one day I said, take away 2 from both sides. Right? I told you what to do. So you say, take away 2 from both sides. So you do, and you say, well, x equals 4. And the next day I came to you and I gave you that. I said, solve that equation. Right? So what would you do? Take away 2 from both sides. So on the one hand, I told you what to do, and the other time I told you what you were doing. You were solving the equation. Well, that's kind of what we were doing here. In this problem, I give you this, and I say, take the antiderivative. And so you did that. Now I'm saying to you, solve that differential equation. How do you do it? Oh, by taking the antiderivative. See the connection there? All right. So that's kind of what's going on there. All right, let's do another one real quick. Y prime equals 2x minus 7. So the solution to that, remember, again, it all goes back to these 2 lines up here. What is a differential equation? It's an equation with a derivative in it. And the solution, so if I ask you to solve a differential equation, keep in mind, the solution is the original function. It's a new meaning of the word solution. So y equals what? Plus c. That is the solution to that differential equation. Okay, so those are the most simple type of differential equations there are. The ones we can just take the antiderivative to get the solution. All right. The second type we're going to talk about is a differential equation that we can't solve by antiderivative, but we will memorize the solution. Now, there's only going to be 2 of them, and I'm only going to tell you one now, and the second one will be in a later chapter, okay, like chapter 4, okay? And then by the end of the year, we'll be able to actually solve it, okay? We'll know how to solve it. But for right now, we're just going to do this one right here. Y prime equals k, which is just some number, times y. If we get a differential equation that looks just like that, we can't solve, first of all, why can't we solve it by doing an antiderivative? What's different about this one? It's got y in it. It's got the actual function in it. Now we know that because it says y prime, so we know y is the actual function we're looking for. That's in there. The other ones all had x's in it. So if we have, so to be able to do number 1, we have to have x's in there in our differential equation, or t's. Sometimes differential equations use t's for the input, sometimes x. So if you have x's or t's in there, you can just do antiderivative. But if it's got a y in there, the actual function, we can't do that. It doesn't work. Okay? Well, so what we're going to do is just memorize the solution for that. Now, this is a really famous differential equation, and the reason we're talking about it right now is we're talking about exponential functions right now. The solution to this is actually an exponential function. It's y equals a, which is just some other constant, e to the kt. Now, we use t here in this problem instead of x, because this is exponential growth. This, or decay if the k is negative. This is exponential growth. So the solution to this is an exponential. Now, one of the most useful times for exponential growth is like bank interest, compound interest. Okay, this is something you probably did last year in advanced math. Compound interest, exponential growth. Now, why is this differential equation represent exponential growth? Well, think about what this is saying. This is something we're going to do more of tomorrow. I think there might be one homework assignment that talks about it a little bit. If we were going to put this into words, I would use rate of change here instead of slope. What this says is the rate that y is increasing or decreasing, let's say increase now if we're talking about growth. The rate that y is increasing is proportional to, this is something you probably talk about in science class with this, proportionality. The rate that y is increasing is proportional to the amount that is there. The amount of y that you have. In other words, the bigger y gets, the bigger y prime is going to get here. Does that make sense? Well, in bank interest, that's what happens. The rate your money grows is proportional to how much money's there. So this describes very neatly what happens with exponential growth? The rate of growth increases as the amount gets bigger. Okay? So, we don't know how that solution comes about. It doesn't come about by antiderivative. So we're just going to memorize it. Okay, so if we, and I'm going to do that here, we'll do it in a minute. So if I give you a difference equation, because I think in your homework there is one. If you have a difference equation that looks like that, you're just going to write down that solution. And then they might ask you some more questions about it, but that's how you get the solution. Okay, so here we actually do an antiderivative. Here we just write it down from memory. All right, here's the third type. The third type of differential equation we'll have is a differential equation that we can't solve and must be given the solution. Now, what we're going to do with that, the questions we're going to do in a problem like that is we're going to verify or see if the solution is actually a solution. Now, here's, again, the analogy I would make to maybe a 7th grade. Before you get into algebra and before you get into solving equations, your teachers may have given you a problem like this. Remember those questions? They give you an equation and they say, is x equals 4 a solution? Well, how do you tell? You put 4 in for x and see if the two sides are equal, right? So before you learn how to solve these things, you did some of this. So that's what we're going to do with a problem like this. We'll have a differential equation we don't know how to solve. They'll give us a proposed solution and they'll ask us, is it a solution? Well, what will we do? We'll plug it in. Okay? And so let's do one of those right now. So, we already did a couple examples of these that we can solve. All right? And we've done, well, let's do one like this. Well, number 2 is so easy. Let me just write off to the side here. So if I gave you a problem, y prime equals 0.06y, right? Can everybody recognize that that's number 2, right? It's got the y in it, not an x, and it's got a k, some number in front. So therefore, the solution to that is y equals ae to the 0.06 t, because that 0.06 is the k, and that k out in front of the y is the same k that's in the exponential up there. So, I mean, that's about all there is to do on those. Now, they might then ask you they might say, let's say we put $100 in at the beginning, right? Let's say we put $100 in. How much is there, 7 years later, right? So, but before we do one of these verify ones, let's do that. So let me expand on that. So let's say we had this, and so we know just from memory that this is ae to the 0.06 t. All right. Now let's say that they told you that this was a bank interest situation. You're getting 6% interest. By the way, that's where the 0.06 comes from in this problem. So you're getting 6% interest compounded continuously. That is exponential growth. Now, the a we don't know. That's kind of like the plus c. Now it's not. It's times. How come it's times and not a plus c? Well, that's something we're going to know. So don't worry about it right now. Sometimes they'll give you some extra information. And that's what they gave you when I said, let's say you put $100 in the bank at the beginning. That's that right there. Now this is kind of like, think about this now. We're starting with a y prime and we're writing the y. So think about when we did that with graphs. When we had an f prime graph and drew the f graph, where did we draw? We had an f prime graph, wanted to draw f. We draw it anyway. That's that plus c part, right? We didn't know where to draw it. But what happens if they gave us a starting point? Then that's where we would start. And now it couldn't be anywhere. There's only one answer. That's how you find the plus c. Well, that's what we're doing right here. They gave me the y prime, but they told me one point on y. We started with $100. Well, what are you going to do with this? plug it in, right? So for y, I'll put 100. And for t, I'll put a 0. E to the 0 is 1. Oh, that's easy. So a is 100. Feels like we're done. That's another thing about these solution things. A lot of times you get a is 100, oh, you're done, right? It always feels like that when you're solving equations, when you find that you're done. Well, no, that's not what we want here. What we want to do is now put the 100 back in for the a. And now we got e to the 0.06t, because what they usually do on these questions is they say 6% interest. Here's your differential equation. You put $100 in at the beginning, and how much do you have 7 years later? So what do you do next? Put a 7 in for t. What they're asking is, now what's y of 7? Right? They told you y of 0 is 100. Now they want to. This is called an initial condition. Right? That right there, IC. This, of course, is a differential equation, a DE. When you take a DE plus an IC, you get an IVP. Makes sense, right? DE plus, I'll show you this just because in your book they're going to say, solve this initial, solve the IVP. You know, what is it? Solve the IVP. Well, IVP is simply a differential equation, and they've given you an initial condition. So all that means is, look back here now, right? See these right here? When we solve a differential equation, like in number 1, we get a plus c. But if they'd have given me an initial condition to put in, I can plug that in for the x and the y, and I can figure out the c. That's all that is. Okay, an initial condition they give you, you can figure out the c by plugging it. Okay? They call that an initial value problem. So don't get thrown off with the terminology. That's what that means. All right, so then we would end up with this, and then we could plug a 7 in, and we could end up with answering that question, how much money is there 7 years? Okay, that'd be more of a calculator one at that point, right, where you could plug that in. All right, let's do this, this third example. What's one that we can't solve? We must be given the solution. All right, so let's say we had this differential equation, y prime plus 2x equals y minus y double prime. Is that a differential equation? It's got an equal sign. It's got a derivative. Right? It's a differential equation. Got a couple derivatives. Right? So that is a differential equation. We have no earthly idea how to solve that. We can't just do an antiderivative because it's got y's in it and all kinds of mess of stuff. It's not like number 2, which is that special one that we'll just memorize. So we have no idea. This is why you take a course in differential equations, all these different types, you learn how to solve. Okay? Well, so here's what this question would be like. This question would be like what I just said over here. Okay? They would say, is y equals x cubed plus 2x a solution to that differential equation? That's what they will ask. Or they might say verify that this is a solution. Okay? Now, we got to be a little more formal in how we do these than we would back in 7th grade. 7th grade, a lot of you in your head, 4 plus 2 is 6, 6 equals 6, you say yes. Okay? Now, if your 7th grade teacher was really strict, they might make you do this. I call this a T chart. Kind of makes a T. Right? If your 7th grade teacher was really strict, they might have made you do this. They might have made you take that 4 and replace the X and write it out. That's not that strict, I guess, but, you know, whatever. They might have made you do this. 4 plus 2 is 6. Oh, okay, yep, 6 matches 6. Yes, it is a solution. Right? And they might make you show that work. All right? Well, we're going to do the same thing here. Is this a solution? Now, notice how I wrote it, though. Remember, differential equation, the solution is the original function. So we don't have a 4 to plug in. We have a function to plug in. So is this a solution? Well, we're going to plug it in. So we're going to make a T-chart. So I'm going to put that line right there. And I'm going to plug in this function. Now sometimes because we're plugging an equation into an equation, it gets confusing on what gets plugged there. Just think back to the 7th grade example. What gets plugged in? The solution gets plugged in. Is 4 a solution? We plug in a 4. We're asking if this is a solution, we're going to take this and plug it into there. Okay? Well, where are we going to plug x cubed plus 2x? We're going to plug that in for the y. So I'm going to put that right there. What am I going to put in for y double prime? I'm going to have to do the derivative, and over here is y prime. I'm going to have to do the derivative of this solution. So I'm going to have to do y prime, and what is that? 3x squared plus 2, and I'm going to have to do y double prime, which is 6x. Those then are going to go in over here. And so for y prime, I'll put 3x squared plus 2, and then 2x, I'll just leave that, right? There's nothing to put for the 2x. Kind of like over there in the 7th grade example, there's nothing to put for the 2 and 6. They just stay there, okay? But I plug those things in. So what do I get over here? Over here I get, I get 3x squared plus 2x plus 2. There's nothing more I can do there. On this side I get x cubed minus 4x. Are those two sides equal? No. So the answer is no, it is not a solution. But that I want to see that work somehow. Now, do you have to do a T-chart? No. But in my experience, when people try to explain why it is or is not a solution, they don't give a very full explanation of why it is. They skip a lot of steps of what's going on in there. And it's not obvious to see why it is. I want it to be obvious. I don't even want you to stop here. I don't want you to stop here and say, well, no, those aren't equal, like because you're doing it in your head. Right? I want it to be so you could show it to a 3rd grader and they could tell if these two sides are the same. Right? They either look exactly alike, like on the 7th grade example. I wouldn't want you to stop with 4 plus 2 and 6. Right? I'd want it to be, oh yeah, there's a 6 there, there's a 6 there. They're exactly alike, those two sides, so it's yes. All right? So that's verifying that something is a solution. All right, so that is differential equation. What we're going to do with differential equations, there'll be a few little things, but you'll have some homework problems you can do. All right, the next thing we're going to do is kind of different. So let's stand up and take it 90 seconds. What the heck? Brain research, be darned. We'll get an extra 30 seconds.
So she lets me leave.
Okay, let's have a seat. So, take differential equations, kind of tuck that over on one side of your brain, so you can quickly recall it when we start working on homework. But, preferably the left side, right? Isn't that the mathematical side? The logical side, left side. So now we're going to come back to the chart and the max min and those kind of ideas with derivatives. Okay? And so we're going to talk about global max and min. Global max and min. Now these two things are kind of unrelated, this differential equation thing and this global max min thing. And so why are we doing them now? Well, it's about the functions we're talking about. Exponential functions, you notice there is a very special function. It is that special differential equation that we just memorized the solution. So it's a good time to talk about differential equations there, just because it matches up with exponential functions. Okay, that's one reason. And then sine and cosine is section 2.7, the trig functions. And sines and cosines have a lot of humps and bumps and inflection points. They have a lot of chart kind of stuff going on. They got local max mins and concave up, concave down, all kinds of things going on there. So those are good things to talk about with the trig functions when it comes to derivatives. So that's kind of why these things are being done right here. And they all involve derivatives. But now we're going to talk about global max min. What is a global max and min? What about the whole graph? Highest point and the lowest point. Now, it might be at a local max or local min, right? Like, for example, in the sine graph, how many local maxes are there? Infinite. And x equals pi halves. X equals 5 pi halves. X, right? I mean, and think about this. Now, we just got to doing it on the test. When we do a local max min, we talk about where they are. And there's an infinite number of them. Now, usually we have a closed interval, so we're only talking about from here to here. So you might have one or two or none or whatever. But we talk about where they are, so we give the x-coordinate. But now let's think of the sine curve again. What is the global max of the sine curve? Give to everybody. But don't give them out if you don't have enough for everybody. What is a global max? Oh, he just ran out. Liar. 50 years old. I can take it, so I'm not sure.
Are you saying about one?
No. That's okay. I can still take. Global max. Okay, so what was the question? So what is the global max of sine? Okay, one. A couple people said it. Everybody else is watching Cody, but okay, the global max is 1. Now, notice the difference there. It's the y value that we answered there, right? Now, some of you didn't answer anything, but pay attention to what was said. That's right. 1. There's one difference right there in global max and min, a huge difference in how we give our answer. And there's still some of you on the quiz on local max min, you're giving me an ordered pair of coordinates. We don't want that. Answer the question. It says, where is it? We want the x-coordinate. If we say what is, notice how I ask the question. Normally with global max min, the question is what is? Now sometimes just say identify. Identify the local max min. Well, then they want the x-coordinates. Identify the global max min, they want the y-coordinates. Okay, it's the highest point and the lowest point. So, sometimes we care where they are, sometimes we don't, but the question will dictate that. But we're always looking at the y value when we want to talk about global max min, because we want the highest point and we want the lowest point. Okay? So now we got to talk about where to find those. So this is going to be related to local max min, but it's different in how you work it. Parts of it will look the same, but then it kind of veers off and it changes. So let's talk about global max min. Like if I had a function that did this, right? How many local max mins are there? How many global? There's only one. This y value right here would be the global max. Now where's the global min? at the far left endpoint. Now that's interesting because we've never had local maximins at endpoints. Matter of fact, we never will. Because to be a local maximin, we got to check on both sides. We got to see if it's going from decreasing to increasing, right? Maybe the whole number line thing. So we won't ever have local maximins at endpoints, but global maximins can be. Here are the global maxes up here, which of course, what's happening right there? What's happening right there? Slope is zero. Stationary point, the derivative is zero. That's, of course, where we do our number line. That's where we look for local max and mins. We're going to look there for global max mins too. But we're also going to have to look at the endpoints. Now, think about a function. Are there any other places that the highest and lowest points could be, other than whether derivative is zero or at an endpoint? Infinity. Okay, let's talk about that a minute. What if you don't have endpoints? What if they don't give you a closed in interval, like x cubed? What's the highest point? Well, there isn't one, right? Because infinity is not a point, right? I mean, it's an idea. It's not really a number. It's not a point. So what we would say is there's no global max, and there's no global min. Now, most of the time, we will have a closed interval. And it's a fact that if a function is nice and smooth, now here's what I thought some people might say, is what about a sharp point? Could that be a global max? Could that be a high point? At a sharp point, the derivative is undefined. Now later we'll talk about that. We would also have to look where the derivative is undefined. But for right now, I'm throwing enough at you the way it is. We're going to talk about nice smooth curves, no sharp points or breaks or weird things. Okay? So the only places that the highest and lowest points can be, and infinity doesn't count because it's not a highest point, it just goes forever. So if I give you a closed interval, there has to be a highest and lowest point. Does that make sense? If it's a nice smooth curve, no breaks or weird things, there has to be a highest point. Because, well, I talk about weird things. What if you had a graph that did this and had an open circle at the end? Is there a highest value there? Let's say that y value was at 2. Let's say this hole was at 2. Is there a highest y value on that graph? Now wait a minute. Some of you are saying yes awful quick. What's the highest y value on the graph if that hole's at 2? 1.9?
Right next.
What do you mean right next to 2? 1.999? How many nines?
12.
Oh, 1.9 repeat. Well, this brings up an interesting thing.
That's equal to 7.
Who said it? You said 1.9 repeating? Well, that's wrong. That's why I ignored it. But that's a great idea because you're right. It can't be 1.9 because you can always go higher. Remember I talked about getting out the door, go halfway, then go halfway, then go halfway? Can't you always get a little closer to the door? No matter where you are. Now, at some point physically, right? But I mean, if you think theoretically, no matter where I am, not going out the door, couldn't I always get a little closer? Absolutely. Can't you always get a little closer to 2 without touching 2? Absolutely. You can always get a little closer no matter where you are. Whatever number you have, 1.99999, you can always add on to it a little more. Now, you said 1.9 repeating. Let's talk about that. What is 0.1 repeating? I thought you guys maybe knew this. Isn't that 1/9? What's 0.2 repeating? 2/9. So you see the pattern. What's 0.9 repeating then? So what's 1 and 9/9? 2. So 1.9 repeating is 2. You guys didn't know that?
No.
Oh yeah. 0.9 repeating is 1 because it's 9/9. 0.3 repeating is 3. I can't believe you guys went this far. I never knew. Wow, we got to look at our math group. Somewhere down the line, we should. Somewhere we should have talked about that. Mr. Sandy. Okay. Sandy. Okay, I'm gonna email Sandy. That'll be a good email. I'll just email. I'll just say, what's 0.9 repeating? What in the world? Where did that come from? I calculus that's all blaming you. Yeah. Yeah. That's another one of those weird infinity things that happens. It is kind of mind-boggling. So go home and ask your parents, what's 0.9 repeating? It's 1. So 1.9 repeating is, yeah, that didn't work for you very well. Okay, 1.9 repeating is 2. So that doesn't work. So you can always get closer. So here would be a case. So why were we talking about this?
So would it be 1.8 repeating?
It wouldn't be 1.8 repeating because 1.9 is bigger than 1.8 repeating. What's that? Infinity's not enough. It's an idea. It's a dumb idea. All right, listen. Listen. So,
We got real close though, right?
all right, now, okay, back to what we were talking about. Global max. So what I was saying is if you have a closed interval, including both endpoints, there is guaranteed to be a high point and low point. If you add in holes and breaks and jumps and things like this, then all of a sudden that might not be true. So we're going to stick with nice functions right now that are always defined everywhere, no breaks and no limits, not existing, no sharp points even. We're not going to have any of that. Just everything's going to be good. Then if that's the case, then there is guaranteed to be a highest point and a lowest point. Yes. Say that again. After this hole, and then it did do that, yes, then you'd be fine. Yes, then you'd be fine. All right, so back to what we were saying. So if we have a nice smooth curve, nothing weird going on like holes and those kind of things, then there's guaranteed to be a highest point and lowest point in a closed-in interval. Now, where can it be? Well, we just said, it could be at the end point like it was down here, or it could be where the derivative is 0, like at a local min or a local max. Those are the only places it can be. All right, you guys think about it, see if you can come up with any others, but it can't be. All right, as long as there's nothing weird going on with the graph. Those are it. So for your notes, this would be what we'd want to write down. So a global max min is the highest and lowest point in that interval on the graph, and the two places it can be is at the endpoints, so we'll just abbreviate that, or where f prime equals 0. So we've already done that with chart stuff. With local max min, where do we start? We do the derivative, set it equal to 0. That's what we're looking for. That's where the local max mins would be, where the derivative is 0, stationary point. So we do the derivative, set equal to 0, solve it, do a number line. Well, we're going to do something similar here. We are going to have to look where the derivative is 0. But we're also going to look at the endpoint. Now, how do we find? So that's where we look for the high and low points. How do we tell if something's the highest or lowest point of that function? I mean, we've got this function f, and we want to know if 2 is the highest point. What do? No. It doesn't have anything to do with the derivative. You're making 2r. Just plug 2 into the function. Listen, if the endpoints are 0 and 2, and the derivative is 0 at 1/2, the highest point has to be at one of those places. So the way you tell which one of those is the highest is you plug them into the original function and look at it, compare it, and see which one is the biggest. Right? I mean, that's it. It's really that simple. We're just looking for the highest y value and the lowest y value of the original function. So we plug them in. Now, what's a little different about that is when we're doing number line, we plug those numbers from the number line into f prime, because we're looking where f prime is positive or negative, so we can tell all that stuff. But in this, we're going to plug into the original function, because we're just looking for the highest y value and the lowest y value. So you just got to know what you're looking for in what you're going to do. Now, we're going to call these our candidates. Right? These are the places that the high and low can be. These are the places that the global max min might be. To tell which one's the highest and which one's the lowest, we're going to do a list then of candidates. I usually just abbreviate it LOC. We're just going to do a list of candidates. That means plugged into the original function. Plug them back into the original function. All right, so let's see what this looks like. So let's do a problem here. All right, this is problem number 37. In your homework, you're going to do 2 of these. You're going to do 39 and 44. 39 is no calculator, which is we're going to do here. And then 44 is the same, looks very similar, but it would be with a calculator. So we'll talk about the differences as we go through this. Okay? All right, so here's our function, and we're going to be doing it with some trig functions here. So this will be the quiz. I think I mentioned this yesterday. This will be the quiz where you're for sure going to have to know your unit circle. You're going to have to be able to do some trig stuff with a no calculator situation. Okay, and maybe even with a calculator situation too. And we talked about how to do that yesterday, right? We talked about how to put the less than at 0 to 2 pi kind of thing in your solve, right? So you got to be able to do that. But let's do a no calculator here. So here's our function. And the problem says find the global max min from 0 to 2 pi. All right? So what did we just say? Well, the global max min has to either happen at the endpoints or where the derivative is 0. Now the endpoints they already gave us. So I'm going to go ahead and start already my list of candidates over here. So I'm just going to have f of 0, and I'm going to have f of 2 pi here. I could do them right now. Let's just wait to the end. Okay? In other words, what I'm going to do is I want to see if my left endpoint is the highest. Well, how am I going to do that? I'm going to plug it into the function and see what my y value is. I'm just going to compare y values to get my max and my min. All right. So I'm going to have those. But I also need to check where the derivative is 0. So we're going to do the derivative. So this part starts out just like a local max-min problem. What's the derivative? 1/2 plus cosine x. And then I'm going to do what? Set it equal to 0. So in a problem like this, you'd probably get a point right there for doing that. Right? Doing your derivative, setting it equal to 0. Now, if this was a calculator one, you can now get on your calculator, do a solve, write down what x equals, right? If it's a no calculator, you probably subtract 1/2 from each side, like we did on yesterday's worksheet, and you ask yourself, where does cosine equal negative 1/2? Well, if we go to the unit circle, cosine is negative over in these quadrants here. Negative 1/2, what is it? It is 2 pi over 3. Now let's review that just real quickly. Remember your special values for sine and cosine. One is root 2 over 2. Well, that's pi 4. That's the easy one, root 2 over 2. The other one is 1/2 and root 3 over 2. Now, the way I remember this generally is which one's bigger, 1/2 or root 3 over 2. Root 3 over 2 is bigger. It's like 0.8 something. 1/2 is 0.5 something. So the way I like to remember this, again, cosine is x, right? What? What
What's
is
the
that?
something after 0.5?
0.5 something. Zeros. But that's something. Zeros are something. Zeros aren't nothing.
We did the zero repeating.
Zero. Yes, it is. That's zero nice. Zero ain't nothing. Zero's something. All right.
Oh.
All right. So cosine in the unit circle, cosine's the x, sine's the y. So 1/2. That's the shorter. So that means when I go on my x, I'm going to go shorter and up farther. So that's the one that's up here. That's pi thirds. The one where you go longer and up shorter, that's pi 6. I don't know. That always helped me remember that. So when you're doing 1/2 square root of 3 over 2, that's how I think of it with the x and the y. But anyway, so that's 2 pi thirds. And then the other one would be 4 pi thirds down in the third quadrant. Okay, 2 pi thirds, 4 pi thirds. All right? And because we're just looking from 0 to 2 pi. So those are my stationary points. Those are the other places that I could have a local max or min. Because back to my picture over here, well, I erased it accidentally. But local max and mins, right, are going to happen either at an endpoint. You're going to have your smallest or biggest y value at an endpoint, or you're going to have it at a place where it peaks out where the slope is 0. Okay, it's got to be at one of those two places. So I'm going to add to my list of candidates here f of 2 pi thirds and f of 4 pi thirds. So this is where it differs from a local max-min problem. A local max-min problem, we would do a number line. And we would check both sides of our stationary points to see when f is increasing or decreasing. So we plug into f prime to see when it's positive or negative. And you may have to do one of those on our next quiz as well with the trig function, right? So we might do a local max-min problem with number lines, or a global max min problem, which is a list of candidates. Understand the difference because you're finding different things. All right, so you approach them differently, even though they are a little bit related. So if this had been a calculator one, you probably could have skipped this step here, wouldn't have to think of the unit circle, you just could have typed it in and solved it that way. Now we're going to take these and plug them back into the original. If you have a calculator, that makes that part of it easier as well. Okay, but it's the same process. You would still show almost all this same work. You would still need to have what you're solving here. You'd have to list your stationary points here. You'd have to have your list of candidates written down here. Okay, you'd have to have all that. Again, I saw this on the quiz, not very often, but a few people on the local max min problem, I saw some things where people just had an answer. Where's the function increasing? He had an answer. Where's the local max min? Had an answer. Had no number line, had no derivative, set equal to 0, none of that, which didn't look anything like a problem we ever did. I'm guessing you just graphed the function, looked where they were, and wrote that down. You can't do that, right? It's got to be this way. So here's our list of candidates. Now, plug a 0 in. That's pretty easy. 0 plus 0 is 0. Now, in the no calculator, sometimes you do have to do a little bit of estimating, some calculating here to get these. Okay, you need to be able to. We put a 2 pi into here. What's 1/2 times 2 pi? Pi. Sine of 2 pi. Sine of 2 pi is 0. So pi, that's roughly 3.14. Right? Because we're going to compare. So we probably need to turn these into decimals a little bit so we can compare. We don't have to be real exact, usually. All right, 2 pi thirds, let's put that in there. What's 1/2 times 2 pi thirds? 2 pi over 6, which reduces to pi over 3. Now what's pi over 3? About 1. 1-ish, right? Pi is 3 divided by 3, so it's about 1. Plus, what's sine of 2 pi thirds? So go back to our unit circle. Sine of 2 pi thirds would be the y value, that's root 3 over 2. That's about 0.8, 0.86, something like that. So we'll call it 0.8. So that's root 3 over 2, okay? But that's about 1.8. Well, that's not higher than 3.14, and it's not lower than 0, so, okay? So that's good enough. 4 pi thirds, 1/2 times 4 pi thirds. 2 pi thirds, right? 4 pi. Now, if you had to write it down, write it down. 1/2 times 4 pi thirds, that'd be 4 pi 6. That'd reduce to 2 pi thirds. Okay, plus, what's sine of 4 pi thirds? That'd be down here. Negative root 2 over, or root 3 over 2. So this, let's see, 2 pi is about 6, divided by 3 is about 2. Take away 0.8, that's about 1.2. So our max would be, I would just put pi. So our max value is pi, and our min value is 0. Because what we want is the y values here, not where they were. Usually we want, now if it says give both coordinates, then I would have written f of 0 equals 0 is the minimum, and f of 2 pi equals pi as the maximum. But if they just say what are the min and max values, then we can just give the value. Okay, that's a global max min problem. So it's related to a chart problem. The difference is on a chart problem we're doing number line. Because a number line tells us everything we need in a chart. If you go back to a chart, everything that's in the chart can be gotten from a number line. If f prime is positive, you know it's going up. If it's negative, it's going down. And where it switches is your local max and min. If you want inflection points, you do a second derivative number line. If it's positive or negative, you know where it's concave up, concave down. If it switches, you know you've got an inflection point. Everything in the chart can be done with an f prime number line or an f double prime number line, and you can find that stuff. Everything in there you can find on the number line, which you do with the derivatives and set them equal to 0. Okay? For a global max min, it's endpoints and where the derivative is 0. They're candidates. You check those by doing a list of candidates. Highest is your global max, lowest is your global min. Okay? There you go. All right, so you can have the last bit of time for your homework. on this sheet, it's just the grouping below the one you did for today, so there's 2.5, which is a little bit of differential equation stuff. There's a lot going on here, a lot of different things, so, you know, I tried to keep it limited a little bit to the amount you have to do here, but it take a little bit of time to go through these things. There's not very much new I have to tell you about before our next quiz. No, it's that next grouping. So 2.5 is the ones on the differential equation, so it'll, like that T-chart, kind of verify kind of thing. Some of that. 2.6 is some exponential, so that probably has a little bit of the differential equation, kind of bank interest, probably stuff with exponential. And then 2.7 is the trig section, that's those two problems I told you about. 39 is just like we got done doing, 37. If you're gonna start with that one, what the heck? 39 is just like that one, no calculator. 44 is just like that, except with the calculator. What's that? Tuesday.